So I guess for the folks that are here, does anyone have any questions about any of the topics in number theory or the counting work that we did so far? If not, we could dive into just going over the test questions.
I do have a question actually.
Yeah, what's up?
I think we were learning something with Mr. Matthew on Wednesday, and I didn't really understand, but class was almost ending, so I didn't want to like go over it again and like take everyone backwards. I'm not sure what it's called, but we were discussing like numbers. There were some dots, and I think we were trying to convert them into numbers. Something like that.
Was it base number conversion?
Yeah, base number conversion, sorry.
Okay, I could go over another example. Let's wait on that just a moment. Maybe actually, here's one thought. Maybe what I will do is later today, make a video presentation showing a couple of examples of base number conversion, and then I'll post that video on the message board.
Okay, that works. Thank you.
You're welcome.
I had a request. We did the sum of factors of numbers with Mr. Matthew, and I wasn't able to really grasp that topic very well.
Let's take, let's see, that was like problem number 12, right?
I think, yeah.
Okay, let me pull that problem up. Okay, so let's say that we want to find the sum of all the positive divisors of 450. Now, all of those divisors, well, first, let's take the prime factorization. 450, what does 450 equal?
I had it here.
3 squared times 5 squared times 2.
So what we're looking for are all the divisors in the form 2 to the E1 times 3 to the E2 times 5 to the E3. And in this case, E1 can be 0 or 1. E2 can be 0 or 2. And E3 can also be 0 or 2. So we want to find some way to take all 18 divisors and sum them at once. And it turns out that we get exactly that if we add together all the possible powers of 2, multiply that by all the possible powers of 3, and multiply that by all the possible powers of 5. All right, do you see that if we do the multiplication term to term, we get, for instance, 2 to the 0 times 3 to the 0 times 5 to the 0. And we would get 2 to the 0 times 3 to the 0 times 5 to the first. And 2 to the 0 times 3 to the 0 times 5 squared. And in every, we multiply each and every one of the different kinds of powers of 2 and the different powers of 3 and the difference of powers of 5. And we get every single one of these combinations of the exponents. So let's stop here for a moment. Is that clear?
Yes, please.
Okay. Now, if we wanted to, we could just go ahead and compute these numbers, which are 3, That's 1 plus 2. And then 1 plus 3 plus 9 is 13. And then 1 plus 5 plus 25 is 31. And multiply this together and we get 1209, I think. Let me know if anybody has a different result there.
Yeah, I got 1209.
Good. And if we wanted to also, we could see each of those three groups of powers of 2, 3, and 5 as a geometric series. And so what some people do is represent those as sums of geometric series. And I'll perform one of those computations. Let's say that we wanted 5 to the 0 plus 5 to the 1 plus 5 squared. And let's name the beast, we give it a name, and then we multiply that by the common ratio. And then what do we do with these two equations?
You cancel out.
We're going to subtract them, and most of the terms will cancel out when we subtract. Second equation minus the first. And so, actually, I'm not even going to simplify. I'm going to just write it like that. And then we can say S equals 5 to the third minus 1 over 5 minus 1. And so if we had wanted to, we could have expressed the sum of the divisors of 450 as 2 squared minus 1 over 2 minus 1. We always get one more power, right, than we started with. Then 3 to the third minus 1 over 3 minus 1. And 5 to the third minus 1 over 5 minus 1. So we could also do the computations this way, but we'll get the same numbers, 3, 13, and 31, and multiply those together.
Okay. Thank you.
You're welcome. Any other questions about this? Okay, who has another question?
I don't have a question about the divisors, but I had a question about the 10th question on the test. It was related to divisors, the even divisors of 20 to the power 20.
Okay. So what's the first thing that we want to do with a divisor counting problem?
We want to find the amount.
Yeah, we want to prime factor. How do we prime factor 20 to the 20th power? Oops.
2a to the power 2 times 5, and you put a bracket in to the
So here, all of our divisors are in the form 2 to a power and 5 to a power. So we have one model for all of the divisors at once. And then we note that E1 is at least 0 and no greater than 40. E2 is at least 0 and no greater than 20. So now, what must be true about the prime factorization of an even divisor?
It would have it would be a multiple of 2.
It would be a multiple of 2. What does that mean about the exponents?
they must be even.
The exponents don't have to be even.
Yeah, it's just there has
Means
to
2
be.
can only have a power of 0.
Okay, Can you say that again for me?
2 can only have a power of 0.
It's not that 2 can only have a power of 0.
Oh, sorry. Okay, let me think through it.
That every divisor has to be multiplied by 2 at least once.
There needs to be at least one power of 2. So the exponent e1 must be at least 1.
Yeah.
And now we want to count these. We want to count the number of ways that we could fill in the divisors. Whoever drew on the screen, go ahead and erase for us. Thank you. So how many different ways are there now that we can fill in numbers for E1 and E2? How many possible values are there for E1?
At least one. I mean, 40.
40, right,
One
yes.
40, yeah.
Yeah, there are 40 possible values of E1. And how many possible values of E2?
20.
21.
21, because 0 works. And then what do we do with these numbers?
Add them.
You multiply them.
We multiply them because each value of E1 can be paired with the value of E2 to create one possible prime factorization. And just to give an example, suppose we had, suppose we had 8 powers of 5. We could have 1 power of 2 and 8 powers of 5, 2 powers of 2 and 8 powers of 5, 3 powers of 2 and 8 powers of 5. For each possible power of 5, we can pair it up with 20 different powers of 2. No, sorry, 40 different powers of 2. And so that gives us 40, and that's true for each one of the values of E2. So we multiply those together, and our answer is 840.
Sir,
Yes.
please, is it possible, if, because I have like quite a lot of schoolwork to do, so is it possible if I could skip this class and catch up on the YouTube video?
Well, you can always watch the video.
Okay.
We'll post I'll post a video of this.
Okay. Thank you.
You're welcome. It's easier if you're here and you ask questions, but office hours to me is less mandatory. But this is a great time to ask questions to get a better grip on whatever it is that you didn't learn is completely the first time. And I said I was going to go and do a video on base numbers, but I take that back. We can go ahead and discuss that here. We'll discuss the 2 problems that we have, and maybe I'll also produce a video later to go through some more examples.
Yeah, I don't mean to pile on, but I also have a question about 11. It's the factorial series question. I was pretty confused by that.
Okay. Wendy will do that one after I do the base numbers.
Okay.
So let's take a look at this one right here. The base 5 numeral, 1, 2, 3, 4, 5. And let's start by just asking, what does that numeral mean? Well, 1, 2, 3, 4, and base 5 is where we have the digit 1 with 3 powers of 5, the digit 2 with 2 powers of 5, the digit 3 with 1 power of 5, and the digit 4 with 0 powers of 5. And maybe that's easier to do from right to left. The units digit, you don't have any groupings of powers of 5 yet. And as you go left, you have 1 more each time. So with 4 digits, we go up to 3 powers of 5. And at this point, we just do the multiplication. Oops. Getting ahead of myself. So it turns out to be easier to convert numbers from other bases to our base. The lengthier process is actually to convert from our base to other bases. And we will do an example of that now. In one direction, it's all multiplication. In the other direction, we have to do division, repeated division. And there are different ways of going about this. Here's the way I generally go about it. I want to ask, how many groupings of 9 are there? Remember when we put beans into bags, bags into sacks, sacks into boxes, boxes into crates, and group them, each time with whatever the base is. So in that first grouping, I ask, how many 9s are there in 2020? And when we do the long division, we get 224 remainder 4. And what that means is that 2020 can be expressed as 224 9s with a remainder of 4. And then I'm going to take those 224 groupings of 9, and I'm going to group those into groups of 9. So 9 into 224, and we get 24 remainder 8. In other words, 224 is equal to 24 times 9 plus 8. And then group those 24 into 2 groups of 9, remainder 6. And of course, those last 2 don't make any further groupings. Oh, those last 6, sorry. And so what this number is in base 9 is, well, we've got, oops, 2 of the largest grouping.
Aren't you supposed to rather divide the 24?
Sorry?
Aren't you supposed to rather divide the 2? Like you did 9 divided by 6, which will give you 0 remainder 6. But isn't it supposed to be 9 divided by 2?
Oh, yes, you're right. I was right the first time, wasn't I? And now all these remainders give us those digits, because there are 2 groupings that we combined 3 powers of 9, where we grouped 3 times over. There were 6 groupings 2 times over, 8 groupings 1 time over, and 4 left over that weren't grouped at all. And maybe I should walk through it this way. If I had just gone one step at a time through all the groupings, I would have said, hey, 2020 is 224 times 9 plus 4. Then that is equal to, we take 224 and turn that into 24 times 9 plus 8, that times 9, and then plus 4. And that means that we have 24 times 9 squared, 8 times 1 power of 9. I'll go ahead and write that 4 times 9 to 0. And then we turn that 24 into 2 9s and a 6. And for shorthand, we just stop writing all the powers of 9 because they just go one down at a time. And we just write the digits 2, 6, 8, 4. And we write a little 9 down here to remind us that we are in a non-standard base, something other than the base, the decimal base that we usually write in.
Mr. Crawford,
Yes.
can I introduce this method that we are taught at school? It's basically the same thing, but it takes less space when writing.
Yeah, I wrote more here than I needed to, mostly just to explain what it was that I was doing. You know, if I were writing this, on my own paper, I just would have written, approximately that right there on the left.
Mr. Crawford,
Yes.
please, I think there's an easier method. That's when you divide 2020 divided by 9 to the power of 3. And then 9 to the power of, then you divide that remainder by 9 to the power of 2, and then 9 to the power of 1, and 9 to the power of 0. You keep on dividing the remainders.
Right. So some people prefer that method. I don't, just because it requires us to go ahead and compute powers of 9, right? And let's say that we have a bigger number. Let's say that the number was 80,423 or something like that. Then I need to compute 9 to the 4th power, which is 6,561, and then 9 to the 5th power, which is 59,049. And now we're doing long division with 5 and 4-digit numbers. And to me, that's a little tedious. I prefer the grouping where I just repeatedly divide by 9 over and over again, because now I'm doing long division with just a 1-digit number over and over again.
But the method I was talking about basically takes just 5 lines when writing.
Well, mine was 4 lines with writing. If you just look at what I wrote in blue, that's all you'd need to write on your own paper. I was writing more here just because I wanted everyone to understand where this comes from.
Okay.
Do you want me to do one more example and show what my work would look like alone?
Okay.
Okay. Let's say that we were going to convert 2020 instead of to base 9, let's say it's to base 6. So this is what I would do. And feel free to kind of race me on your own paper using your own method. Can erase here. Sorry. And so, it took me just because I don't do this computation much, took me a moment to do to realize what I was doing with the very first computation. But something that you practice like this just a little bit, You can probably do it in just 5 or 6 seconds, maybe. And that's not too bad. But to do it the other method would have required computing up to 6 to the 4th power. And then starting with long division. And then computing 6 to the 3rd power. But ultimately, here's my belief with something like this. The most important thing is that you understand what's going on. The most important thing is you understand the grouping of the digits into powers of whatever the base is. And so long as that is the case, you're going to be fine. Oops. Oh, no, that was 0. Okay. Any other questions on this one? Have I done all my arithmetic correctly?
I think so, but I just, is that supposed to be a 1 beside the number, or like the 3,204 supposed to be a 1?
Sorry, I didn't write that very close together, did I? That's the first digit. This would be 1 times 6 to the 4th plus 3 times 6 cubed plus 2 times 6 squared plus 0 times 6 to the 1st plus 4 times 6 to the 0.
But why would we put a 1 over there?
Speak up a little for me.
But please, why would we put the 1 over there? Because all of those are remainders, which you have put.
Yeah, I could have said, hey, 6 into 1 is 0, remainder 1.
Okay, I get it. Thank you.
Yeah, sorry. Whenever I get to my last remainder, I stop dividing because I know that last one is already there. But yeah, that's where we get our 5 digits. I'll make a video with a few more examples and I'll post that later. I apologize if this is one of those things where to me your exact arithmetic process doesn't matter as much as understanding that you are grouping by powers of the base. And if you want to compute out 6 to the 4th and divide, that's fine. But I prefer the one grouping at a time. Any other questions? Oh, somebody was asking about 11. Wendy, I'll let you take that one.
Sure. Let me just turn on the screen share. Can you enable screen sharing, Matthew?
Oh, there we go.
Thanks. Let me try again. Everyone see that? Okay, I think the video is just lagging a bit.
I can see. Okay, yeah, I can see it.
Okay, this is number 11, right? I just have it. Is this the problem?
No.
Okay, I'm gonna take that as a yes. It's just because I have just the combinatorics up. All right, cool. So for this question, we're asked, what's the units digit of the sum? And it's definitely very unwieldy to calculate this whole sum. So let's think about how we could do this without actually computing out the sum. And so we could write out a couple of the initial factorials just to kind of see what's happening. So for example, we know 1 factorial is just 1. 2 factorial is 2 times 1, which is 1, or sorry, which is 2. 3 factorial, 3 times 2 times 1 is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. And then 5 factorial, we have 5 times 4 times 3 times 2 times 1, which is 120. So we notice that for 5 factorial, we actually have a 0 in the units digit, which is interesting. If we have 6 factorial, we actually know 6 is 6 times 5 factorial. And so we know 120 is 12 times 10, which is 6 times something that ends in a 0, which means that this also ends in 0. 7 factorial, we kind of have the same thing. It also ends in 0. And so the reason for this is things that end in 0 have 10 as a factor. And we have factorials, if there's a 2 that divides that and a 5 that divides that, that means 10 divides that, which means it'll end in 10. And so what we are seeing here is that all these numbers, 5 factorial, 6 factorial, 7 factorial, and on, all the way to 987 factorial and even beyond, all of these will end in a 0 in the units digit. So then if we want to find the units digit of the sum, that means we can sum up the units digits of each of the elements. So for 1, that units digit is 1. For 2, 2 factorial, that units digit is 2. For 3 factorial, that units digit is 6. And for 4 factorial, that units digit is 4. And then for everything else, it's going to be 0. So if we sum up all of this, we get 13. So the units digit is actually going to be 3.
That was very helpful. Thank you.
Yeah.
I have a question. Could I please ask you right now?
Yes, go for it.
Yeah, so I was really confused on question 9.
Can you remind me what question 9 is?
Oh yeah, sure. It says numbers that read the same forward and backward are called palindromes. How many 5-digit numbers are palindromes?
Gotcha. I think that one was one of mine. Let me see which, one sec, let me just look up which number that was. Okay, cool. So I think that was this one, right?
Yeah.
All right, so basically, as it said, it reads the same forwards and backwards. So let's just make sure we understand what palindromes are. So I'll give a couple examples of palindromes. So if I have something that's like 1, 2, 3, 2, 1, that's a palindrome, because if I read it from right to left, it's 1, 2, 3, 2, 1. And also if I read it from, sorry, if I read it left to right, it's 1, 2, 3, 2, 1. If I read it right to left, it's also 1, 2, 3, 2, 1. Another example might be something like 3, 3, 3, 3, 3. It's also the same, whether I read it forwards or backwards. So here we want to count how many different palindromes there are that have 5 digits. And again, we want to do this without sort of having to list all of them out. So let's think about if there's any restrictions to these numbers here. So we have 5 digits here. What are the possibilities for the first digit?
1 to 9.
Right. So on this leftmost digit, it can't start with a 0 because otherwise it's not a 5-digit number. And so here it could be 1 through 9. So there's actually 9 possibilities. What about for the second digit? Are there any restrictions on that if the first digit's 1 through 9?
No.
0 to 9.
Yeah, so this is 0 to 9. So there's 10 possibilities here. What about the middle digit?
0 to 9 also.
Yeah, that's right. What about the fourth digit?
It has to be the same as the second digit.
Mm-hmm. So it has to be whatever this is. And then what about the last digit?
It has to be
the
the
same
as the first digit.
digit.
Yeah.
Yeah, right. So if so basically whatever this is, you can't really choose any other ones. There's only one choice for that, and same for the last one. Another way to think about it is the number has to be of the form A, B, C, B, A, where A, B, and C are different digits, and there's choices for A, 10 choices for B, and 10 choices for C. And so if we multiply these together, we get 900. Any questions on this one?
Yeah, I got the same answer,
Mhm.
and I used Caseworks to do it. I first like created a case of ones, and then I realized that like each set or number, that when it starts with 1, like each case would have 100 numbers. So then since there are 9 of them, I multiplied it by 9.
Yeah, that works too. It's kind of the same idea here. It sounds like what you did was sort of say, okay, if the first digit is fixed, like say we pick A, or say you have something here, then there's 100 choices for the rest, and then you notice that there's actually 9 different cases for the first one. So then you multiplied by 9. So it sounds like you just grouped that one first and then multiplied there. Any other questions on this one?
I don't have a question on this one, but I have another question from the test. Should I ask that?
Go ahead.
Okay. It's question 20, and it says the permutations of A, H, S, M, E are arranged in dictionary order as if each were an ordinary 5-letter. What is the 86th?
Okay, I can do that one because it's also, oops. I think it was one of the later ones. Here we go. All right. Just to kind of explain the question a little. So if we arrange something in dictionary order, it means it has to be in alphabetical order. And if we start listing out the permutations of these letters in alphabetical order, we would start with something like A, E, H, M, S, and then A, E, H, S, M, A, E. Just write a few. I won't write all. M, H, S. And so on. Does everyone see why that is? All right.
Are you
so,
just arranging it in like order for it to be like any ordinary 5-letter word?
So basically, we look at all the permutations of A, H, S, M, E. I guess like first question, how many permutations are there of A, H, S, M, E? Does anyone know?
25.
Why is that?
Because it's 5 times 5.
Why is it, or why did you decide to do 5 times 5?
Because, oh, sorry. Okay, let me think you that.
Okay.
I think it's 120 because 5 factorial.
And can you explain why it's 5 factorial?
Yes, because there are you have 5 different options to choose, and you have 5 different places to put it. So then it becomes 5 factorial over 5 minus 5 factorial, which is 5 factorial over 1 factorial, which is 5 factorial.
Yeah, so I guess to explain a little bit, if we want to sort of permute the letters A, H, S, M, E, there's 5 choices for the first letter, 4 choices for the second letter, 3 for the third, 2 for the fourth letter, and then whatever is last, there's just 1 choice for the last letter. So we have basically 5 times 4 times 3 times 2 times 1, which is 5 factorial total permutations. And then what I'm doing in this list is I'm just writing down the permutations in dictionary order, so it's alphabetical order. And so the ones that are sort of earliest alphabetical are the ones that start with A, basically the letters that come first in the alphabet, if we were to order them. So basically this question is saying, if I were to keep writing out this list, like say I wrote down all the way to the 86th word, then what is the 86th permutation? And so I wrote down a couple just to give the idea, but we're actually going to solve this without writing down all 86 because that would take a long time. And so one way to think about this is kind of breaking it into kind of like cases. So the first thing we would notice is if we wrote everything in dictionary order, then all the ones at the beginning would start with A. And so one sort of sub question is how many permutations of A, H, S, M, E start with A? Does anyone have the answer for this?
Is it 4 factorial?
Yeah. Can you explain why?
Because then there will only be 4 letters left. So the first one could only take 1 out of the 4. Second will only take 1 out of 3. The next will take 1 out of the 2, and the last one will take the last one left. So which becomes 4 times 3 times 2 times 1, which is 4 factorial, and that's equal to 24.
Yep. So there's 4 factorial or 24 words that begin with A. So if I wrote down all of the letters and all of the words in alphabetical order, I would first have to write down 24 words that begin with A. And then after that, the next letter in alphabetical order is E. So say I write down a bunch of things that start with A, then I would move on to E. How many permutations start with E?
The same as the number of A, because the same number left, so the same distribution.
So there's also 24 that start with E. Cool. And then what's after E? So I write down all the ones that start with A. I write down all the ones that start with E. I've written down 48.
H.
And then we kind of have the same number here. So we have 24 that start with H. So here I've written down 48. Here I've written down 72, which is getting pretty close to 86, which is the one we want. So after H, we start writing down M. And so what I could do at this point is there's only sort of, there's 14 more, but I also don't want to write down 14. So let's see how we can count beyond that. So when we start with M, then the first dictionary ordered or sort of lexicographically first permutation that starts with M would be M-A-E-H-S, because the rest are in order. So my question is, if we have M-A, how many permutations start with M and A? Because the first ones that start with M, this first subset of that, the second letter has to be A.
That's 3 factorial.
Yeah, that's 3 factorial. So that's 6. So at this point we've written down 78 permutations. And then what's after that? M-E? How many start with M and E?
Also
This is
6.
3 factorial.
Yeah, also 6. So I'm just adding here. So if I write down all the permutations of MA and then ME, then I've written down a total of 84. And so what's the next one after that? The 85th one.
MH.
Yeah, so it'd be MH. And then what's the first one that starts with MH? If we were to arrange in alphabetical order.
M-H-A-E-S.
MHA.
ES, right. So that one's the 85th one. And so this question asks for the 86th one. So what's the one right after that?
M-H-E-A-S.
MHASE.
Oh, S-E, yeah, sorry.
Yep, that's right. So this is the answer.
Could you please keep it here? I want to just copy something quick.
Yeah, sure. Let me zoom out a little so you can see the whole thing. Any other questions on this problem or any other problem that you all wanted to go over?
Well, should we just wrap things up here then?
No, can you please go to question 25?
Sure. Was that one the frog one?
That's the frog problem.
Okay.
Yes.
So where's the screen? Okay, here you go. Cool. So did everyone understand this problem? So basically it's saying we have this frog that's moving along a number line. And at any point it can go from, go to the next multiple of 3, or it can go to the next multiple of 13. And then it wants to know how many different, the question wants to know how many different move sequences are there before it gets to 39, which is the first multiple of 3 and 13. So this is one that I think we could solve with casework, because there's a bunch of different like ways that or different like sequences of moves that the frog could use to get to 39. and there's not like a really obvious way that I could count them all at once. So I might think about, okay, how do I get to different numbers within different numbers within the number line before I get to 39, so I can kind of sum those together. So one thing we can think about is like, does the frog get to 13, or does it not get to 13? Does it sort of bypass 13? And then does it get to 26, or does it bypass 26? So basically, does it visit each multiple of 13? And so one way that helped me think about this one is I wrote down kind of this tree of the frog has to start at 0. And then it could take a sequence of moves and arrive at 13, or it could take a sequence of moves and sort of bypass 13. And the way that it would bypass 13 is it would do 12 and then go to 15. And then let's just say that it gets to 15 through 12. And then once it gets to 13, it can either go through 26 or it cannot go through 26. So let's say it goes to 27 through 24, because it has to go from 24 to 27, or it can go from 24 to 26. And then similarly, in the case of 15, it can go to 26, or it can go to 27 through 24. And then once it goes from 26, it has to take some sequence of moves to 39. Once it goes to 27, all of these have to go to 39. And so this just helped me organize like my casework a bit to see, you know, what are the cases I want to count for, and make sure I'm only counting everything once. So now we can start counting like how many different ways are there to get through each branch of this tree. And then we can sum everything up together once we're done. So now that we've broken it into different cases, I'll use a different color. How many ways are there to get from, let's do the right side, which is a little easier, 0 to 15 without going through 13? Does anyone know the answer to that? Okay, so I'll explain this one. So basically, there's only one way to get from 0 to 15 if I don't go through 13, which means I basically have to keep visiting every multiple of 3, right? Because if at any point I decide to jump to the next multiple of 13, I've gone to 13. So basically, there's one way to do this, which is just 0, 3, 6, 9, 12, 15. If I look on the left side, I want to count how many ways there are to go from 0 to 13. And there's actually a bunch more ways I could do this. So I could start from 0, and then I could jump directly to 13. Or I could 3 and then go to 13. Or I could do 0, 3, 6 and go to 13. Or I can go 0, 3, 6, 9 and go to 13. Or 0, 3, 6, 9, 12 and go to 13. So there's actually 5 different ways here. Actually 5 different ways here. Does anyone have any questions about what I've explained so far? If not, I'll go to the second part of the tree.
I don't understand, like, how you got there 5 ways.
Okay, so for basically this subproblem, I'm looking at how many ways are there for the frog to go from 0 to 13 on the number line. And remember, the frog at any point can move to the next multiple of 3, or it can move to the next multiple of 13. And so in this case, I'm saying, okay, the frog starts at 0, and then it could either go directly to 13, or it could go to 3. If it goes to 3, it can also then go to 13, or it can go to 6. If it goes to 6, it could go to 13, or it could go to 9. If it goes to 9, it could go to 13, or it could go to 12. And then if it goes to 12, it could go to 13, or it could go to 15. So then I wanted to count how many ways there are to get to 13, and then how many ways there are to get to 15 without going through 13. And so if I go to 13, there's actually 5 ways that I can get to 13. And then there's 1 way I can get to 15 without going through 13.
Then how do you know which number to choose? That's in 15.
Can you explain the question a little bit more?
Why didn't you say from 0 you could go to 13 or 3? But instead you said you could go to 13 or 15. Why didn't you choose any number but 15 and 13?
Oh, so I chose 13 because for cases here, there's only 3 multiples of 13 that the frog could or couldn't visit. And so in order to break it down into a manageable number of cases, I decided to break the problem down into, does the frog visit 13? Does the frog visit 26? And basically use that to count the cases. And then I use 15 because that's the next multiple of 3 after 13. If I pick something like 3, then it's not really, it's hard to compare that with like, did the frog visit 13? So really I'm trying to compare, did the frog visit 13 or did the frog not visit 13? And then did the frog visit 26 and did the frog not visit 26? That's my cases.
Okay, I get it. Thank you.
Okay, so this is how I got 5 and 1 for this branch of the tree. And then now we could look at this, now we could look at this left side. Okay, that didn't really work. Look at this left side over here. So I'm at 13. How many ways can I get to 26? And then how many ways can I sort of not get to 26? And so maybe I'll just write it out down here again. So say I'm at 13. Then the next step I could take is I could go directly to 26 because that's the next multiple of 13, or I could go to the next multiple of 3, which is 15. Similarly, at 15, I can go directly to 26, or I can go to the next multiple of 3, which is 18. At 18, I can go directly to 26, or go to the next multiple of 3, which is 21. At 21, I can go directly to 26, or to the next multiple 3, which is 24. And then at 24, I could go directly to 26 or to the next multiple of 3, which is 27. And so we see that from 13, there's again 5 ways to get to 26. And then there's sort of 1 way to get to 27 without going through 26. So basically not going through 26. So I'm going to fill this out. There's 5 ways to get to 26, and then 1 way to not go through 26. And then we can do the same thing on the right branch over here. So if I start with 15, I actually draw this out here. And out this tree over here. So if I start at 15, there's 4 ways to get to 26, and then 1 way to not go to 26. So here, there's 4 ways and 1 way. And then now let's look at getting to 39. So I'll write it out, but it's the same idea. And so if you were trying to do this really fast, you could probably just see it's similar, it's 5. But if I'm starting at 26, then I can go directly to 39, or I can go to the next multiple of 3, which is 27. Go to 39, or I can go to 30. I can go to 39, or I can go to 33. I could go to 39, or I could go to 36. And then from 36, I have to go to 39. There's only, that's the next multiple of 3, and that's the next multiple of 13. So there's 5 ways to go from 26 to 39. And then again, we can see this sort of here. We've also counted how many ways there are. From 27 to 39, there's 4. And so I can fill out, here's 4 and 4. So now we've kind of figured out in all of the cases how many ways are there to get from 0 to 13, and from 0 to not go through 13, how many ways there are to get from 13 to 26 and not through 26, and similarly not through 13 to 26 and not through 13 or 26, and then to 39. So now we can put everything together. And so to kind of summarize it or put it in another way, this branch of the tree is saying that I start from 0, I visit some sequence of numbers, I visit 13, I visit some stuff, I visit 26, and then I visit some stuff, I visit 39. And so in order to count how many total paths there are, visit all of these points, I can multiply these together. So 5 times 5 times 5, which is 125. Now if we look at this path, this is saying a different case, which is I visit 0, then I visit 13, then I don't visit 26, and then I visit 39. And so here we see there's sort of 5 ways to get from 0 to 13. There's 1 way to get from 13 to 27, and then there's 4 ways to get from 27 to 39. So this is 5 times 1 times 4. This is 20. Over here, this branch is saying the case where we have 0, then we don't go to 13, so we go 12, 15, and then we go to 26, and then we go to 39. And so there's 1 way to get here, 4 ways to get here, and then 5 ways to get here. So this is 1 times 4 times 5, which is 20. And then the last case is we have 0, and then we don't visit 13, and then we visit 26. So then we have 20, 24, 27, and then we go to 39. And then here, we basically have 1 way to go here, 1 way to go here, and then 4 ways to go here. So that's 4. So these are the 4 cases. And then to get the final answer, we actually just need to sum up all the 4 cases, because there's this many paths in case 1, this many paths in case 2, this many paths in case 3, and this many in case 4. So if we sum all of them up, we get 120 plus 20 plus 20 plus 4, which is 169. So this one was a bit long. Does anyone have any questions?
Please, is there an easier way or faster way to do the same question?
There's different ways that you could break up the cases. I think this one is like pretty fast. You don't actually have to write down all these trees. You can think about like, okay, if you can kind of quickly see there's only 1 way to get from 0 to 15 if I don't go through 13, because I have to keep going through multiples of 3. You can also see that there's kind of 5 ways to get from 0 to 13 without writing it out by saying, okay, I could either go 0 to 13 directly, or I could go 0, 3, or all the way to 12. So there's 4 multiples of 3 under 13, or I could go directly, so that's 5. So you can do kind of these, like, you can count without having to draw out the whole tree, or you could draw out the tree once and kind of see there's a pattern, because as you saw, these trees all are kind of the same. So there are sort of faster ways you could reason through it. I don't know, Matthew, is there like a way that you thought of for this one?
Oh, I apologize. I let you took this one, and I was reading.
Oh, that's okay. The question was just, is there a faster way to do it? And so to me, I thought this was the most straightforward way for me to think about it. But if there's like a faster way other people think of, we can also post in Piazza. I would say this is like one of the harder problems I put on the test. So I would expect that it takes longer than, say, the first problem I put on the test.
If I haven't worked this one yet, but if I work it and I come up with something that looks easier, I'll post a video.
Sounds good. Yeah, oftentimes there's also like multiple ways to solve a problem, and then some people might find it faster to think about it one way than the other. So, yeah.
It may be, and I actually don't know exactly what your solution is, but it may be that you can make a grid that's like a path walking grid, and then just use the go backward casework method. Is that clear, or is that what you've done here? Or?
No, I didn't do that. I basically, I mean, maybe it maps to the same thing, but I basically just had cases where it would go through each multiple of 13 or it wouldn't. So
Right.
there's like 4 total cases.
Are there questions about any of the other problems?
Yes, question 6.
Okay, I'll take that one.
Okay, cool.
Okay, so it's easier for me to think in reverse of the relationship. We're looking for where n is a divisor of a perfect cube, but I would rather say we are looking for a cube that is a multiple of n, which is a multiple of p q squared r to the 4th. So it's going to have at least 1 power of p, at least 2 powers of q, and at least 4 powers of r. So, and the biggest reason why this is a good way for me to think about the problem is that we're focusing around prime factorization, which is often a good model for thinking about problems involving multiples and divisors. So the key here is this restriction. We're looking for a perfect cube. And so I asked the question, what is the prime factorization of a perfect cube look like? So let's just play around and take a look at a couple of examples. Let's say we want the prime factorization of 12 cubed. Well, 12 is 2 squared times 3 to the 1st. And if we cube that, we get 2 to the 6th times 3 to the 3rd. Or perhaps we want 2020 to the third power, which has two powers of 2, a power of 5, and a power of 101. And when we cube that, we get 2 to the 6th times 5 to the 3rd times 101 to the 3rd. And we could try a few more examples, but I'll go ahead and ask, what do we notice about the prime factorization of any perfect cube?
All the exponents are multiples of 3.
All of the exponents are multiples of 3, right? And that happens because we multiply exponents. And in this case, we are always multiplying each one of them by 3. So, then the other question I might ask is there a one-to-one correspondence? Now, we know that it's true that actually, we don't need the one-to-one correspondence, do we? We just need to know that the cubes have, actually, it's probably good. We may be able to do this on an individual case, but we'll go ahead and establish a one-to-one correspondence. We know that all cubes have exponents in their prime factorization that are multiples of 3. Is it true that all prime factorizations that have exponents that are all multiples of 3, is it true that all of those are perfect cubes?
Yes.
It is true. And to demonstrate that it's true, we could take a look at, I'll show one example and then I'll show generally how this works. If we had, for instance, 2 to the 3rd power times 3 to the 6th power times 5 to the 12th power, we could rewrite that as 2 to the 1st times 3 to the 2nd times 5 to the 4th, all taken to the 3rd power. And this is because we could divide 3 out of each of those exponents. We're just going in reverse. More generally, if we have a prime to a multiple of 3 power times another prime to a power that is multiple of 3, so on and so on, any number of these, we could rewrite it as P1 times P2, P1 to the E1 times P2 to the E2, all the way up to Pi times to the EI, taken to the 3rd power. So we can uncube as we divide each one of those exponents by 3. So every perfect cube has only exponents that are multiples of 3, and anytime we have exponents that are multiples of 3, we have a perfect cube. Though we didn't even really need to go that far to answer this question because of the way the answers are given. But up here, well, actually, I'll go ahead and just do this. Well, we need a number of powers of 3 that is at least 1, but is a multiple of 3. So we need 3 of them. We need enough factors of q, the prime q, enough powers of q to be a multiple of 3. We need at least 2 of them, but we need a multiple of 3. Smallest possible would be q cubed. And we need at least 4 powers of r, but we need a multiple of 3, so we go up to r to the 6th power. And all of this is p times q times r squared to the 3rd power. Are there any questions about this one? Okay. What other problems would any of you like to take a look at?
Could we discuss question 13?
Sure.
Thank you.
Okay. So we're looking for 4-digit integers in base 10. I'm not going to convert them to base 70. I'm just going to get a grip on what it is that we're looking at. We're looking at this list of 9,000 4-digit numbers. and then maybe we start converting. You know, I'm just going to start with 1,000. Let's say we want to convert 1,000 to base 7. I go, okay, what's 7 into 1,000? That's 142, remainder 6. 7 into 142, well, that's 20, remainder 2. 7 into 20, that's 2, remainder 6. And then 7 into 2, which is 0, remainder 2. So 1,000 is equal to 2 times 7 cubed plus 6 times 7 squared plus 2 times 7 plus 6 times 7 to the 0 power, or 2626 base 7. Similarly, 1001 is 2630 base 7. 1002 is 2631 base 7. Once we've converted one, we can just kind of count up, which is kind of nice. But here we've discovered the first one that we want right here. And it happened where we have a units digit of 1. Well, what that means is the very first time that we divided by 7, kind of like here when we were converting 1,000, that very first time that we divide by 7, we get a remainder of 1. That's where that units digit comes from. In other words, what we're trying to do is count the integers that are 1 more than a multiple of 7. So the integers that are 1 more than a multiple of 7. Well, we found the first one. We know that 1002 is equal to 143 times 7 plus 1. If we count it up by 7, we get 144 times 7 plus 1. And we're going to go all the way up. We need to find around where we end up. Then we'll have a simple, then we can convert our list to a simple list and count them more easily. 7 into 99 is 1, 4, 2, 8, remainder 3, I think. Somebody can check my arithmetic, please. Tell me if I'm correct or not. So now we have this list, and notice that it's, well, you know, we have this list, and I could write it like this. And Wendy went over ways with all of you to go through operations to create a simple list, but it's actually pretty easy in this case. If we subtract 1 from all of them, we end up with a simpler list, and then we can divide that list. Oh, wait a minute. That was a 7, not a 9. Pardon? And now we can divide each term in this list by 7, and we get 143, 144, 145, up to 1427, 1428. And now we can subtract 142 from each of these. Well, we can just use the formula that that you all derived with Wendy. And let's see, what do we get? 142 from there. 1286, I think is what I get. Any questions or thoughts about this one?
Yes, I actually understand. Thank you. But could you like just scroll up a bit? I have like a about something in the beginning.
Sure.
So when we converted the 1,000 to base 7, we got 2626 base 7, right?
Mhm.
Then how come if we're just going to count up by 1, how come 1001 was like 3 more than that and not 1?
Okay. Let me write this using the digits, and we'll talk about this. So base 7 is the base. So there's a kind of alien squid out there that has 7 tentacles. It doesn't have 10 fingers like we do. It has 7 tentacles that it counts with. And it can only use the digits 0, 1, 2, 3, 4, 5, and 6. When it counts up, it has to round. Right? In base 7, we group when we get to 7, not when we get to 10. There is no digit 7. There are just the digits 0, 1, 2, 3, 4, 5, 6. So when you count up from 6, you group, and that's when you group to the next, we call it the 7's place instead of the 10's place, perhaps. But I'm going to actually walk through an example of counting up in a small base, just to give you an idea. Let's say that we're counting in base 3. On the left, I'm going to count in base 10. And on the right, I'm going to count in base 3. On the left, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, in base 3, it looks like this. 1, 2, and now we go ahead and carry 1, 0. There is no digit 3. We group every time we get to 3. 4 is 1, 1. 5 is 1, 2. 6 is 2, 0. 7 is 2, 1. 8 is 2, 2. 9 is 1, 0, 0. We group by 3, and then we group by 3 again, and we're at a new digit place. So 12 is 1, 1, 0, base 3. And to think through this counting process in another base, it's a little bit disorienting at first, right? We're so used to carrying when we go beyond 9. We're just so used to it that it almost tricks us to learn to think differently, and it takes a moment. But do you feel comfortable with that? Do you see why it is that when we count up, we go from 2626 to 2630 in base 7?
Yeah, I understand now. Thank you.
You're welcome. Any other questions about this or another problem from the test?
Question 15. Can you please go to it?
Okay, I'd seen Wendy and I combined to make this test, and I saw that she had put problem 9 on the test. And so I decided to throw this one on a little bit later as an example of a similar counting problem, but where we have to think in another number base. And the question I'll ask you, Norley, is what are the digits in base 8?
From 0 to 7.
Right. So when we ask ourselves, going from left to right, how many ways are there to choose the leftmost digit? How many are there?
8.
Be careful. There's a little bit of a caveat here.
7.
What was that, Manvendra?
7.
7, right. Because we have an implicit restriction that we can't use 0. So there are 7 ways to choose the leftmost digit. And then how many ways are there to choose the next digit?
7.
And this time there are 8. This time we are allowed to use 0. We're allowed to use 0, 1, 2, 3, 4, 5, 6, or 7. That's 8 possibilities. And then how many ways are there to choose the middle digit?
8.
8. And then once we have chosen those first 3 digits, how many ways are there to choose the next digit?
1 and 1.
1.
Right. These 2 digits are restricted by the definition of a palindrome. Once we have chosen the previous digits, we have to have kind of reflection. So usually in my own paper, I kind of write a star there. But, you know, if we're thinking in terms of multiplication, it's just 1 and 1. So our answer is going to be 7 times 8 times 8, which is 448, I think. Any questions or thoughts about this one? Okay. Any other problems from the test?
One thing I'll kind of say or announce is Joel also helped us grade the test. And so I think everyone should have their test results now. You can check and or potentially your email. You can check now or after office hours.
Let's check question 7.
Number 7, how many different ways can a student guess a complete set of answers to a 7-item true-false quiz? I'll let Wendy take that one.
Sure. I'll just try to explain this one, and then if needed, I can draw something. But basically, we have 7 questions, questions 1 through 7, and then for each of them, the answer could be true or false. So how maybe someone else could, if anyone got this one, how did you think about this? Oh, this is a helpful visualization. So we can see if there's one, I'll just speak along to Matthew's drawing. So if there's one question, there's 2 ways because it could be true or false. If there's 2 questions, you see there's actually 4 ways because the first question could be true or false. And then for each of those, the second question could be true or false. And so to get that, you could do 2 times 2 because there's 2 choices for the first question, 2 choices for the second one. There are 3 questions, then again, we have 2 choices for the first question, 2 choices for the second, and 2 for the third. And so if we multiply those together, we get 8, and Matthew's written all 8 there. So we can kind of generalize this for 7. If there's 7, then we have 2 choices for the first question, 2 for the second, 2 for the third, 2 for the fourth, 2 for the fifth, and 2 for the sixth, and 2 for the seventh. So that would just be 2 times 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the 7th power. So it's kind of an equivalent question to saying how many different sequences of trues and falses can I make if there's 7 of them in the sequence. Any questions?
And of course, later you can ask other questions on the message board, and some of you can answer for each other. I'm going to go ahead and strongly encourage that. If somebody asks a question on the message board and it was one that you were able to solve, practice putting your own thoughts into words. The more that you do that, the more that you verbalize the way that you think, the better you will get at thinking. The relationship between reading and thinking and writing, that feedback loop, it's just one of the absolute best ways to learn and learn a little bit more deeply. Even if you could already solve something, you have to learn it a little bit more deeply in order to express that solution to somebody else. So, do your best to answer each other's questions. If questions go unanswered, we as the instructors can chime in once in a while. And otherwise, everybody have a good weekend, and we will. I'll see you on Monday morning or Monday afternoon for all of you.
My last question, please.
Yeah, which
Number
one?
8.
Number 8. Okay. Yeah, it's funny. In some ways, this is a very basic question, but the way you formulate your strategy is not particularly basic. There are a lot of ways you could go about it, but I'll tell you how it is I thought of going about it. I imagined making a 30 by 30 grid from 1 to 900. And these numbers that we're looking at are the last 2 rows, really. And then, once we have this whole grid, kind of filled out, we can perform the sieve of Eratosthenes. And when we do, we remember what we learned when we were performing the sieve, which is that we really only had to go through the first row. Now, another way of saying that is that we only have to go up to the square root of an integer. We only need to test primes up to that point to determine whether or not the integer is prime. But for me, I actually, I did this in a spreadsheet. Let me see if I still have that up. And I'll show you the spreadsheet that I used. Okay, I do. And I don't have the numbers still up. What I did was I laid the numbers out here in a grid, 10 of them at a time. I filled out that grid, and I went through and I erased all the multiples of 2, and then I erased all the multiples of 3, and then I erased all the multiples of 5 and 7 and 11, 13, 17, 19, 23, and 29. And that's the equivalent of going through the sieve through the first row, those first 10 prime numbers. And whatever remained must be prime. So I look up here and I count 8 of them, and so 8 is our answer. Was that clear enough?
Okay, yeah, thank you.
You're welcome. All right, everybody. We'll see you on Monday.
Have a great weekend. Thank you so much.
You too.
Thank you.
Bye, everyone.
Thank you. Have a great weekend.
Thank you.
Bye. Thank you.
Thank you. Bye.